presentation here, and then her webcam. Monica, you might need to turn on your webcam there. There we are. All right, take it away.
Thank you, Matt. And thank you, Josh. It's an interesting, I just caught the tail end of it. It's very interesting. So thank you very much. Today, I'm here to talk about garbage collection, but it's going to be a little different talk because I'm going to introduce the need of automatic memory management and then give a quick overview into OpenJDK collectors. I'm Monica Beckwith, and I am a JVM performance person at Microsoft. I've been working with the OpenJDK pretty much for all my life. I was working with OpenJDK before it was OpenJDK. So I should say the hotspot VM, basically. I've been working with it for all my life. And so let's get started. So here's a quick agenda. We are going to cover just the basics today, mostly, and then like a quick overview into the GC algorithms. I want to talk about the need for GC and set up why what is automatic memory management, so the allocation and the reclamation part of it, and then provide a few techniques that probably all of us are familiar with, but just kind of put them in the right flow order. So to me, GC is memory management, as I mentioned. And memory management is not only about reclamation, as in to get back heap space in Java heaps concepts, but also it's about allocation. So it's optimizing the space that you have. So allocating and reclaiming kind of goes hand in hand. So if I were to ask you, and if I give you some space, memory space, and then you start allocating in that space, your space would look like this, and then your allocations will begin. And eventually your space will get filled up, right? At this time, we run out of space, so naturally we want to make sure that we can reclaim objects that we don't need anymore, so we don't have to keep them around anymore. So what we end up doing, and because we all know about GC roots, so we'll start from the root set. Okay, so this would be like whatever is your thread local, your static variables. So let's do that. Let's start from your root set, and let's start tracing. So we'll trace from the root set the objects, and that's why we're making our own live object graph right now. And here are the objects that are pointed to by the root set. Okay, they are highlighted here. From that, I try to trace objects that are pointed to from that object. So it's basically any incoming references to these objects are now all highlighted. So eventually all the live objects I'm highlighting here. And it seems to me, because it's a manual process, it seems to me that I'm done. So I can reclaim the objects that I no longer need, right? So which means these objects right here in black. Okay. So I go ahead and reclaim them. But unfortunately, when I was doing the reclamation, I forgot to identify this one object, which because I have left it around, this can lead to memory leak. So if I don't reclaim it ever, it's going to eventually lead to memory leak. And that's one of the reasons why you have memory leaks in your, even on your heap, because you forget that an object is kept live. The other problem is the problem of dangling pointers. So say, for example, I became overzealous, and because I'm manually reclaiming, I reclaim an object that's highlighted in red right there. I reclaim that, and now I have two dangling pointers right here. So there were two pointers, incoming pointers to that object, but because I collected that object, now we have two dangling pointers. So these are the drawbacks of manual reclamation. So the suggestion is to, of course, go with automatic management. couple of examples that I like to provide of automatic memory management is sometimes one of the simplest form is the stack-based allocation. So you do push and pop, and then most of these issues will be taken care of there. For example, we have the Java bytecode interpreter. So it's basically just a stack, right? So push, pop, and that's all you do with that. Then you get a little more sophisticated, then you do something called hybrid allocation. In that case, by hybrid, I mean you basically combine region-based allocations. People also call this as arena allocators. In OpenJDK lingo, we call it the TLABs, the thread local allocation buffers. Basically, the concept is that allocations are region-based, and then you combine that with reference counting or a tracing garbage collector, which is what OpenJDK collectors are. So, and there you have it. You have automatic memory management. Okay. So, as I provided examples already, OpenJDK garbage collectors use TLABs, right? I wanted to provide an overview of both reference counting and tracing, but just to save time, I'm just going to compare them side by side here. So, reference counting, you would use it because it has the lowest overall footprint. Okay, so it's also non-moving. So one of the things that you have to know about OpenJDK collectors is that they are moving collectors. So you move live object from area 1 to area 2, and that's basically the whole idea of reclamation, so to speak. Okay, and I will talk about moving collection shortly. Reference counting is not moving. So basically, you have any incoming references are held in a count. So if you have 5 incoming references, so the count will be 5 for that object, and then you decrement it once references are gone. So, but there is a disadvantage to it, which is that it needs to be able to handle cyclic references. You would have seen reference counting algorithm employed for Androids before the ART, before Android runtime. Right now, it's kind of similar to CMS, but prior to that, it was reference counting, and they knew how to handle cyclic references. On the flip side is the tracing collector, and it of course has a higher footprint because you have to have mark and all those things. So you have to marking arrays and sophisticated algorithms also need data structures. So of course the footprint is a little bit higher. There is also what it provides you because you're tracing and then eventually you're moving it. So it provides you co-location of your objects. So objects that are live together are also co-located together. So it's kind of it's good for your hardware caches. And of course, you don't need any space for counting references. So you don't need that count field for your objects. So if I had to quickly summarize reference counting, I would call it the continuous tracker because it has to be on at all times, because anytime you add or delete a reference, then you have to increment and decrement the count, right? On the flip side, for tracing, it's only active when you need it to be active. So basically, either you run out of heap space or whatever's the generational space, or when a threshold is crossed. And I'll talk more about what that means, because that is really important when we talk about garbage collection efficiency. Okay. So now that we know why we need automatic memory management, let's try to design one. So to design an automatic memory management system, there are a few basic considerations that we should all think about. As I mentioned, collection efficiency comes to mind first. So basically, sometimes it's prudent to just let the garbage be. So, for example, I want to be able to get done with my garbage collection work as quickly as possible so I can make way for the application threads. Especially if I'm in a stop the world collector, I want to get out of the way of the application threads. So an example of this is the incremental compaction in G1GC, which is the first garbage collector in OpenJDK. And it's also known as the incremental compaction phase is also known as mixed collection, where we only have a few old regions that we can include as a part of a collection cycle. And if time permits, I'll go into that as well. The next consideration for designing a GC algorithm would be the performance trifecta, which is basically responsiveness, throughput, and footprint, right? So usually you design GCs keeping, favoring one of the three, maybe two at a time as well. So for example, the oldest collector that you will know in OpenJDK is the serial collector, and that's designed for low footprint. Okay, it's single threaded. Then comes the parallel GC, which has parallel worker threads, and it's designed to do the GC work in a stop the world pause, get done as quickly as possible and get out of the way. So it increases your throughput efficiency. And then the rest are like balanced somewhere between the responsiveness and throughput metric. What other things would you consider? I think then once you go past the basic, you want to be more sophisticated. So you want to take into consideration the generational hypothesis, which is like most objects die young. So you would find generational collectors in parallel GC, G1 GC. So basically all OpenJDK GCs that you may know of are generational except for ZGC and Shenandoah. The other thing that you want to make sure is that you have a way to sieve out objects that are either not going to live long or are not going to be a part of your long-lived transients. So that's called something like that. That kind of notion is called the age threshold. And that helps you promote only the long-lived objects. Sometimes you want to leave the transients, the long-lived transients around. And for that, age threshold also matters because these transients will be aged and kept around for longer if you have your thresholds adjusted properly. So most of the GCs that are generational also understand the age threshold policy. Now, quickly diving into a little bit more details of OpenJDK collectors. So here we have heap layout and regions and generations. So if you know about the Java heap space, it looks like this. It's a contiguous heap space. And then for G1 GC and Shenandoah and every other GC, that the newer GCs that you know of, they're called as regionalized GCs. And they're named such because their heap is divided into regions. Okay. And some of the times you would also hear the concept of generational GC that I mentioned. For example, serial, parallel, and of course G1. It'll basically means that you have two generations. One is called the young generation, and the other is called the old generation. So if you talk about the latest, the default, as well as the two new collectors in the OpenJDK, as in ZGC and Shenandoah, you would find that ZGC and Shenandoah are non-generational, but they are regionalized. And G1 is regionalized as well as generational, as you can see here. So now going back to the concept, so I'm going to try to keep this within G1, ZGC, and Shenandoah. So because we have the generational concept and the non-generational concept, I'm just going to simplify it to the basic form of collection, which is copying. So for all the collectors in OpenJDK, we have, when we're reclaiming by way of copying live objects. Okay, and so we're moving them from one place to the other. So there are many terminologies used: copying collector, compacting collector, or evacuating collector, or evacuation phase. And it basically means that the same heap that you have is divided into from space into space. Okay, and as you allocate, and we talked about this when I was talking about the manual process, right? So you're allocating into the from space, and eventually the from space gets filled. And then, of course, because this is an automatic memory management algorithm, you start from the GC roots, which are your static variables, thread stack, and EJNI references. And then you start marking, live objects. And eventually, you identify all the live objects, and then you move or copy the live objects from the from space into the to space, such that you can reclaim the from space. So now, after reclaiming the from space, you literally swap the from and to spaces. So now your to space becomes the from space, and then your from space becomes the to space. So all allocations will happen now in the formerly to space, which is now the from space, shown in green, and then the promotions, or when you're moving out aging objects, that will happen into the to space on the left. And that it keeps on moving back and forth, okay? And that's how you achieve aging as well. Another concept that I wanted to introduce, as I mentioned, all the newer garbage collectors are regionalized. So let's talk what that means. So at any given time, the entire heap is just a bunch of regions. And these bunch of regions would be either occupied or free. Okay. So for example, here in green, we have occupied regions, and then on the right we had unoccupied regions. So let's see how an active heap may look like. So we have these darker regions that are occupied, and the rest are not occupied. And basically the ones that are not occupied are called free regions. And there is a list maintained by the garbage collector. And this list is basically tells you all the free regions that are available for allocations or promotions. So when you have a generational heap like G1, these occupied regions could be either from the young generation or it could be from the old generation. G1 also has the concept of humongous objects. So these could be also humongous regions. Okay. Let's look at, so now that we know that the heap is basically a bunch of regions and we have either free or occupied regions, let's look at how and when we choose to collect, as in reclaim heap space, okay? So again, going back to the previous examples of the dark regions, let's say that we are able to say that the highlighted objects are live, and then the ones that are not highlighted are not live anymore. So we go ahead and identify the regions that are full of garbage. So we know that the highest return are these regions, because we can immediately reclaim that space, because we really literally have to do nothing. So the major work is moving objects, live objects from region to the to region, right? So for objects that are dead, we really don't have to do anything except for return them back to the free list, right? So that's easiest. So let's do that first. So now we have reclaimed that region, those two regions. The next thing we would find are that these are the two regions that have been identified to have the most garbage, right? They only have one live object in this particular case. So let's co-list them together, and there you go. So we have reclaimed two regions, and we have started adding to a new region right there, and so on and so forth. So basically, the collection priority is to reclaim regions with the most garbage, and G1 actually gets the name from that, garbage first. So let's get the regions which have the most garbage, and that's the first thing we can do. That's quick, easy peasy, and done, right? The next thing we want to be able to do is be able to identify regions that we want to collect before we actually go collect them, right? So this is done in something known as a collection set. So any of the regions that we have identified to be a part of the collection cycle, be it a young collection cycle or an old or a mixed collection cycle for a generational collector, then those regions are a part of the collection set. Okay. So in G1's case, and in even many of the newer collectors, you have threshold-based collection. So the thresholds are basically set on how expensive a region can be. So if it's too expensive to collect a region, we will leave it out of the collection set. If we've already reached our time-bound thresholds, then we will leave those regions, leave the remaining regions out of the collection set. So usually the regions are arranged based on their collection efficiency. Okay, and this is something that I had talked about earlier when I was talking about what are the considerations that we want to have for automatic memory management. So efficiency is one of them. So I give the example of incremental collection, which is also known as incremental compaction or partial compaction or mixed collection. So it's all the same. It just means that you are not going to collect the entirety of a generation, but you will collect it incrementally so that you still respect your pastime goals. Okay, and the way we can do it is basically having these thresholds that I've mentioned. Okay. So after you reach these thresholds, you stop collection. And even if there is a bunch of garbage that's to be left, that it will be left behind. And that's brings us back to the consideration of, let some garbage be. Okay. The best part of it, and then you will see that mostly with the newer collectors, the low latency collectors that we have, ZGC and Shenandoah, that any of this collection, the movement of live objects from the from space to the to space, it doesn't have to be stop the world. So you can do it concurrently, basically, along with your mutator threads, which is mutator threads are your application threads. So along with your application threads, you can actually do this collection, and what that gives you is that the application threads don't have to stop while the GC is doing its work, but also it gives you a little more complexity because now you are literally moving objects when your mutators are trying to access them too. So you have to appreciate the pros and cons. You have to weigh both and see which collector is better suited for your application. But the good news is that it doesn't have to be stop the world. A collection doesn't have to be stop the world. Okay. So quick introduction here, and this would probably be my last slide. What I'm going to do is quickly sort the three new collectors based on regionalized generational compaction algorithm, target pastimes, and if the marking algorithm is concurrent or not. So G1GC is yes to pretty much everything, but the compaction is stop the world. Basically, gets the meter threads to a stopping point and collects the live objects and moves the live objects from the from space to the to space. The target pastime for G1GC is 200 milliseconds. So you see that it's straddling the threshold, the boundaries where it's designing itself for throughput efficiency because of the stop the world pauses, as well as it's trying to have kind of soft real-time goal for the pastimes. Shenandoah and ZGC, I'll put them both together so that we have enough time for Q&A. They both are regionalized. They both are right now not generational, and they both do compaction, and the compactions are concurrently done along with your application threads. They both are trying to meet the 10 milliseconds pastime goal, which is pretty aggressive, and which is why they are considered low latency collectors. And just like G1GC, Shenandoah also employs the snapshot at the beginning marking algorithm, whereas concurrent marking algorithm for ZGC is striped. I don't have time to go into the details, but definitely go read more about it. I may have put some links here. Oops. Well, maybe towards the end. Sorry about that. These are just overflow slides that I wouldn't have time to time to get to today. But I will send out the links if I don't have it here. There you go. Yeah, there you go. So some of the links are here. I'll send out more. If you have any questions, I'll take them now.
All right. Thank you, Monica. So I'm
Cool.
looking in Slack. I don't see any in there. If you have some questions, please post them now. I'll ask a question.
Okay.
What's your favorite part about being quarantined?
I don't know. I'm since 2007, I've been remote worker, like on and off. So I've always been this. The remote part is my favorite part, but it's always been my favorite part of my job. So I would say just being with family. And,
Right.
Yeah, trying to understand and work together with them, which is interesting because usually I had the whole network to myself and everything to myself, but now I have to share with them. So
right. During my talk today, I had to tell everyone get off the internet for 30 minutes, right? I want no damage.
Yeah, it's like even my dogs and stuff like that. I have like locked myself in here, and the dogs are outside. Everybody's outside. It's like nope, because everybody's so used to just like interrupting, especially the dogs. Right. So yeah.
My wife and I've thought of getting a like on-air sign, right, that we could like put by our desk to be like, "Hey, don't interrupt us now."
Live.
Right.
Yep.
Well, thank you so much. We have a break now, and as far as I can tell, it's a long break. It's about an hour, so everyone can go and grab a meal and hang out with your families and come back in an hour. I would say 6:45, but I'm Mountain Time, and I know that not everyone's Mountain Time, so. Could be different for you, but thanks for coming, Monica. I really appreciate it, and we'll see you all in an hour or so.